Hey guys, this is Nitin from FTC Team 18172, Uplift Robotics, and in this video, I'll be walking through the different types of constraints in Creo. In Creo assemblies, constraints are used between two components in order to fix their location within the larger assembly. There are two main types of constraints in Creo, the first of which are static constraints. Static constraints fix components and don't allow for motion. This is useful for things like screws and channels, since this prevents the parts from moving out of place. There are many different static constraints, but the two most common ones are coincident and distance. Coincident connects two surfaces or planes with each other. Distance constraints allow you to set a fixed distance between those components. The second type of constraint is kinematic constraints, which allow a component to move in an assembly. There are many different types of kinematic constraints, each defined by a different set of motion, but the most common ones that we use in FTC are pin and slider constraints. Pin constraints allow for things like wheels and gears to rotate about an axle. Slider constraints are useful for things like linear motion, like linear slides. If you want to learn about all of these different types of kinematic constraints, the FTC Creo documentation has a nice layout of all of the degrees of freedom associated with each kinematic constraint. I'll leave the link for this in the description in case if you're interested in learning more about degrees of freedom and the more complex types of kinematic constraints. And you can always ask our team questions if you want to learn more about these other types of constraints. Now I'll go into Creo and show some of these constraints in action. So now in Creo, in order to use my constraints, I have to assemble components. So I'm going to go ahead and use the assemble command and pick the part that I want to use. So I want to use the outer drive plate that I created from my skeleton video. Open that up. And now you'll notice that it brings up a new tab for component placement. And there's a lot of features here, so I'll take you through them. So the first thing is that there's a drag feature for the translation and rotation of your part, which you can use to move your part around. Over here, there's a drop-down menu for the static constraints, and there's another one for the kinematic constraints. There's also a placement dialog box, which has all of the constraints between your part and the assembly. Alright, so I'm going to go ahead and create a constraint. The first one I'm going to create for this part is a default constraint. So the default constraint takes the default coordinate system from my part and the assembly and constrains them together. And this is good because the first part that you assemble within your assembly should always use the default constraint, and this will allow for the rest of the components to be directly attached to the larger assembly. So now that my constraints are satisfied, I can click the green check mark to exit out. If you ever wanted to edit your constraints, you can go back to the part, click on it, and bring up the edit definition, which is this icon right here, and you can always go back and edit the component placement. So next I'm going to use some other static constraints in order to assemble a bearing. So I'm going to use the same assemble command and click on the 6mm bearing, open it into my window, and now you'll see that my bearing has been placed, and now I need to define some constraints in order to assemble it. So I'll click on the placement dialog box to show you that there's no constraints right now. So since this bearing is really small in the model right now, I can either zoom in and go all the way into the bearing, or I can open it up in a new window by clicking on this command. Now in a new window, it shows it at a much larger scale. So I can click on the edge that I want to use, so I'm going to use this outer diameter, and click on the hole that I want to place it on. So I'm going to use that hole. And next, I'm going to use another coincident constraint for the edge of the flange, and then click on the surface of the drive plate and assemble it together. And now you'll notice that it automatically did the coincident constraint for the last one, but for this constraint, it chose to use a normal constraint. So I don't actually want a normal constraint for this, and you'll notice that it says constraints invalid. I want a coincident constraint instead. So I'll click on coincident, and now you'll notice that there's one last degree of freedom that this bearing has. And in order to solve for this, I can click on the allow assumptions, and that automatically places the bearing. And this is because the bearing was before allowed to rotate in the hole. But in this case, the bearing doesn't really matter in the orientation, since the bearing is the same all the way around. So I can use the allow assumptions in order to fully place the bearing. And now that that's done, I can click the green check mark. And if you notice that the bearing has an orange color to it now, and that's because it's fully assembled. And it also says fully constrained here. So now I can go and click the green check mark. Alright, so now I'm going to start creating a kinematic constraint for an axle. So I'll use the same assemble command and pick the axle that I want. And now, within my component placement, I'm going to create a pin connection. So I'm going to use the kinematic constraints drop-down menu, and I'm going to select the pin constraint. For pin connections, under the placement dialog box, you'll notice that there's two different definitions that I need to have for my pin connection. There's the axis alignment and the translation. So for the axis alignment, if I open it up in a new window, I can select the outer surface of the axle and the inner surface of the bearing. And that'll align the two axes of the parts. For the translation, I can select one of the flat sides of the axle. So I'll select on this flat side, and I can assemble it to the back side of this plate. So I'll select on that. And now you notice that it automatically created the pin connection. So now if I rotate it, you'll notice that the axle can now rotate in the bearing. So there's one more optional reference that you can use for the axle. So I'll click on that, and you'll notice that there's a few options here, but the first thing that it asks for is two different references. So if I want to pick the orientation that my axle is in, I'm going to use the flat part of the axle, the D part of the axle, and use the reference of the top part of this plate. So I'll use those two together. So now it gives me a degree value for the distance, the angle offset from this two references. So if I set that to 0, you notice that the axle has slightly shifted. If I set it to 180, my axle has been inverted. So I'll leave it at 0 for now. There's a few other features here. So I can set that as the 0 position if I wanted to, but since this is already the 0 position, I won't do that. I can enable this to be regenerated every time I regenerate my model so that I have my wheel in a fixed position. So I'll allow that for now. There's also these minimum and maximum limits, but for a wheel, or an axle, I don't actually want a minimum or maximum limits, since this is more for things like servos and linear slides. So this is good for now. So that I have my connection definition complete, I can click the green check mark, and now my axle is fully constrained. I can use the drag components to simulate the motion of my axle, and you can see right here that my axle is turning about in the bearing. For the slider connections, I've taken the CAD files for long robotics slides, which you can find on the Long Robotics website. Right now, I have this assembly constrained using static constraints, but I want my linear slides to move. I can go into the edit definition of the second component, select edit definition, and now I can take a look at the constraints within the placement dialog box. You notice here that it's fully constrained. So in order to convert the static constraints over to a mechanism constraint, I'm going to delete one of these constraints. I'm going to delete this one, this last one. And now you notice that this blue button over here has been activated. And this allows me to convert my static constraints over to a mechanism constraint and vice versa as well. So I'm going to select it. And now you notice that it automatically selected a slider connection. I can also change it to a few other different types of connections, but slider is what I want. And slider connections have two main connections that have to be defined: an axis alignment and a rotation, similar to the pin connection. But instead, the translation is the optional degree of freedom. So for the translational degree of freedom, I'm going to select these two references right here, and this will allow me to set a fixed distance that the slides can move. So for linear slides, there's only a fixed distance that the linear slide can travel up. And for long robotic slides, I know that this is around 180 millimeters. So I'm going to select 180 and enable a regeneration value as well. And that looks good. My connection definition is complete. I can click the green check mark. And now if I go to drag components and select the part that I use the slider connection on, you notice that I can now drag the slider out, and it simulates the motion of a linear slide. As usual, the Creo files made in this video will be in our GitHub repository in the description. If you have any questions about constraints, Creo, or FTC in general, feel free to contact our team through our social media information in the description. Thanks for watching, and stay tuned for more tutorials in CAD, FTC, and more coming soon.